All right. Hello, everybody, and welcome to another OWASP Toronto chapter meetup. We have an exciting presentation for you today with our guest, Philippe Artu. But before we get there, we have a couple of housekeeping items. For starters, if you've never been to any of our meetups before, we have a feedback form in the description of this video. You can use it to send feedback about how we run the show, as well as providing suggestions for future meetups. And if you're looking for CPE credits, leave your name and email address so we know that you attended. Also, if you have questions during the course of this presentation, just leave them in the chat, and we will periodically be checking that and presenting that to our presenter. If you're looking for work or you are hiring, please leave that in the chat now. And our next event will be next month, so stay tuned for more details on that. That's it for me. Philippe, the floor is yours.
Hi everyone, welcome to this presentation on Unicode vulnerabilities. My name is Philippe Artu. Today I'm going to talk about different vulnerability classes that are somehow related to Unicode. So these will be the topic for today. I'm going to start before talking about the different attacks and techniques about key concept around Unicode and UTF-8. So just to make sure everybody understand those key concepts, and then I'll pass to the main content around normalization, case modification, and bypassing web filters with Unicode encoding. So who am I? I'm a researcher at GoSecure. So I do research mainly around application security. I develop open source tool and do some research around new vulnerability classes. So one of the area I work on is static analysis. So these are some of the projects I've worked on previously. I'm also a volunteer at NorthSec. I'm doing challenges for the competition, the CTF, and I'm also doing the website for the past 3 years for the event. Other than that, some of the recent work I've done at GoSecure, I'm doing workshop at different events and conferences, and I've published recently 2 workshops, one on XXC and one on template injection. If this topic is interesting for you, you can find all the content freely, the step-by-step instruction, and the infrastructure that is deployable in one command with Docker Compose and everything. So, and if you're more into reverse engineering, my colleague also, I've done last year a complete workshop, a 2-hour workshop on binary analysis, introduction with Guidra. Very interesting. So if you're curious about those, just look at my Twitter account or the GoSecure Twitter account. It will be linked at the end of this presentation, so you'll find all this content for free. First, we're going to go through a small history of encoding and its challenges. So one of the early encoding format was ASCII. The way ASCII work is for every character we're going to get only 1 byte. So 1 byte being 256 possibilities. The first 32 possibilities will be control characters. So think about terminal needed for a terminal, or delimiting file or string. So like no and a file and other terminal related characters. Then we have standard character set. These are used as printable character, so all character from A to Z in uppercase and lowercase will be in this range. Then we have the extended character set. This is the final part of ASCII, and these are needed for accent character and special characters. Special character, for example, in French we have accent over multiple characters. Same thing for a Spanish character. And these need to be defined in some way. So these are defined in this range. The thing is, this range is limited, so we cannot support all language in 128 characters. And also, for example, in the IBM one include in this screenshot, we have also some UI related characters to be able to draw a window in console application. So the way we're going to be able to support multiple language is we're going to define code page. So code page will, for ASCII, will define what character are included in this extended character set. So if we need to encode a text file for a Russian user, then we will need to use Cyrillic, so that is the code page 855. In North America, the most common code page was the IBM PC1 or DOS Latin US. This includes a French character and a Spanish character, so most user would be covered for North America. There are major limitations with this. We cannot, for example, include two language of two different code page in the same file format. We cannot include, for example, a Greek quotation inside of a text, or same thing for Russian text. We can have also issue because the encoding, the code page are not explicitly defined in a file. So we can, for example, save a file on a US PC, save it on a disk, send it over another country, for example in Russia, and then the file will not be displayed the same. So this is a problem that increases when internet arrives, and suddenly we have a communication between different systems that don't have the same code page by default. So the solution for this, Unicode came with one solution, and it's indexing every character that we know uniquely. So instead of having this rule where 1 byte equal 1 character, we're going to start to become more flexible, and the idea is first we're going to index every character from every language. So Unicode include all Asian, so think about Japanese, Chinese character, mathematical symbol, measuring unit. Also, even some ancient Hebrew and Egyptian hieroglyph are included in Unicode. So a few examples, we have first US ASCII character are all included. We have accent character. We have in the middle, this Japanese character means water. So this is one character in itself. We have a sum, so if we need to do a mathematical equation, we're going to be able to do so with it. And also we have all emoji included in Unicode. One thing to keep in mind is that code point are a unique index. So there will be a number for every character, but this doesn't define the way it will be encoded. So while the index, for example, for A is 41, and the ASCII is in fact 41 in byte, this will not be the case for every character. So same thing for Unicode. So the way a uppercase will be encoded is 41, but it will not be the case for every character. So how do we store thousands of code points into a file? How do we support those thousands of code points? UTF-8 is one encoding, so Unicode has multiple components. So there is the concept of code point, but it also has it defines multiple way of multiple method of encoding. So UTF-8 is one, UTF-16 is another, and UTF-8 is a variable length encoding. This means that not every character will be 1 byte. So one of its objectives was being backward compatible. So all ASCII character in the standard character set will be actually encoded the same way. But every character that would have fallen in the extended character set, so any other special character, the first bit will be 1, So when we're gonna decode those messages, we're gonna know if when a byte starts with the bit 1, then we're gonna be able to parse this character. So we have one example here, the number of bit set to 1 in the first byte will define how many bytes we're using to encode this specific character. So for example, some not Unicode, but emoji character are encoded on 3 bytes. This means that they will start with 1 1 1 0. So 3 1 then 1 0. So UTF-8 is really prevalent, so it's probably the most used, it is the most used encoding format. While there is UTF-16 available and standardized, there is still 8859, which is the default charset of Windows, so this is something to keep in mind. Those stats come from encoding format returned by web server. So aside from maybe a few old IIS and front page server that might be using 8859 by default, this is not that common for web server. This percentage is probably much higher if we would look at the statistic for encoding for a desktop operating system. So, but this is something to keep in mind, because while there is UTF-8 that is widely used, there is still a chance when you're implementing application that a user will save a file, for example, with Notepad here. So because Windows used to have ISO 8859 by default, then once your server will read this file, those characters will not be interpreted properly because it's expecting UTF-8. And because, for example, a plain text file doesn't have encoding defined, then there can be this code confusion. This confusion might not be obvious because, for example, if you open a file in ISO 8859, most code editor will guess the encoding and will open it properly. But your application will have an encoding by default and it will not be guessing most of the time. Now we're going to look at normalization issues. So what is normalization? Normalization is a transformation of Unicode characters with the objective of comparing two Unicode strings that might be equivalent or very similar. So because Unicode character can be encoded in different way to mean the same character, we're gonna normalize and try to reduce or simplify the string, and this way we can compare two strings and have a good idea if it's the same thing visually for the user. In practice, it's mainly used or often used to create some ID for URL by developers. So if you have the display name or the name of the user and you want to create a unique URL that will remove accent, these are often used function. These were not intended for this use case, but that's one place where you often see it. There are two main normalization methods. So there is the canonical way that is really strict. It will try to decompose characters that can be, for example, a cedilla as one symbol or as two characters. So one Latin character and another one with a transformation on the preceding one. Compared to compatibility mode is much more aggressive in some way. It will try to convert many characters to Latin characters. So, for example, scripted H character will become uppercase H. Same thing for exponent. Exponent character will simply become regular characters. So I exponent 9 becomes simply I9. Fraction will be simplified in multiple characters. So 1 quarter becomes 3 different characters, 1/4. And what are the security implications of this? So some characters in Unicode will have implication when they are placed inside of URL or path. So for example, C/O or C/U will become 3 different characters in itself. There will be characters that look like @ but are not the same Unicode character, but once normalized, they will become the Latin version of it that is ASCII-like. Okay, so one example of this flaw was the HostSplit vulnerability that was found late 2019. Multiple browsers were vulnerable to this. Internet Explorer and Firefox, and I think Chrome was also vulnerable. Because browsers were normalizing location header, this introduced a security issue. Location header are the header returned by a web server to create a redirection. So once a server returns this, the browser will change the page to their URL given. But because they were doing a normalization transformation on this value, suddenly a URL like this that would have a Unicode character account of, the character would be transformed to A/C as 3 different Latin characters, and suddenly the redirection is not even made to the same host that we intended it to do the redirection. So let's say that there was a parsing on this URL previously, and we make sure that it was a subdomain of Microsoft.com. Suddenly, because the browser did a transformation, we're not redirecting to the initial host that we intended to. This had implication for example, with OWASP application, because in OWASP, when you're doing a redirection, you're at the end redirecting with a secret token that will be a session. And this session token, if you're redirecting to not the right host, suddenly an attacker could, for example, hypothetically, point a user to log in with a special provider, but this provider, while it might fall into the whitelist, in practice, when it's going to be redirected, it's not going to be a subdomain of Microsoft.com. So URL redirection, this is the main implication for this vulnerability HostSplit that was explained in the paper. There are some other characters that could add implication regarding URL or domain names. So there is this @ symbol that becomes an actual Latin @ symbol. While it looks the same, it is not the same Unicode character, so the application might not be validating here the subdomain the same way for those 2 values. We have also question mark. We have slashes that there's at least 1 character that becomes a slash once normalized, and we have those 2 dots, one above the other, that become ... simply when normalized in compatibility mode. It can be used to create potentially path reversal. In practice, to bypass blacklist, there's going to be some easier way I'm going to show later, but normalization can still potentially be a vector. When I heard about HostSplit, I did a survey of few library and language to see if I could find a similar issue. I found in Oracle JDK that the hostname verification was doing normalization of the hostname to which you're connected in TLS and the template hostname, so the hostname that would be inside the certificate received in the TLS handshake. So here the variable name, it's the hostname to which we're connecting, and the template, it's the the hostname inside of the certificate that can include, for example, wildcard. Because certificate can have a wildcard in their definition. The thing is, because we're doing a transformation before we're doing the match, suddenly we can have multiple characters, as we saw previously, that can be normalized to the same Latin character. So if we are targeting a specific host, then we could craft a malicious certificate by replacing a single character by one that will be transformed to the same, and then the hostname verification would pass without a problem. What are the key recommendations? It's mainly around validation. So make sure you're not doing normalization inside of security component that are doing security critical string comparison. Avoid normalization, and if you are doing normalization after there was some validation or prior, make sure you review the flow properly. You can also do a review of your library you're using, because they might be doing indirectly normalization to URL or path with the intent of simplify the life for developer, to make sure that, for example, the hostname they specified is a valid hostname, but it might have security consideration. Prefer whitelist over blacklist, because as we see, you can have a blacklist of a specific value, but if I replace a single character with one that will be normalized to the same value, then we can circumvent some blacklist. And yeah, having a strict validation can help. Now we're going to look at case modification. This is a very similar process. So it's another transformation that is part of Unicode. So it's going to be the same type of vulnerability. So Unicode defines how every character will look once they are in uppercase and lowercase. So there is a link. Not every character will have a corresponding character, but some have, and some will have a transformed character that will become a Latin character. We'll see a few examples. So for the Latin character A, no surprise, the capital, the uppercase version will be 41. So this is equivalent to ASCII. No surprise. But here we have this special Unicode character that is the German B. And once it's in uppercase, it becomes 2S. So 2 Latin S character. And this is part of the language. So this is the way German work. Same thing for this character called ligature of F and Y. It will become 2 separate Latin characters. Then for the lowercase transformation, we'll have the Kelvin K. So for temperature, so there's Celsius, but there's also Kelvin. And when there's a lowercase transformation, there is no character in Unicode for lowercase Kelvin. So instead, they simply point to the Latin K character. The dotless I, so this is a huge Y, usually there is no dot, will become a small I with a dash on it. So it becomes Latin character I with the surrogate character that is a dash. Some potentially that the second character could be truncated later on, but this is less likely that it will cause an issue in the flow of an application, because it's not all Latin character. So what are the potential issues? This is basically almost the same as normalization. So if you are doing a certain validation, and then after it you do a normalization, suddenly you don't have the value that you expected. It can be used also to bypass some filters. So you have some validation that this is not a certain value, and then suddenly you have a transformation and you can end up having the blacklist value. Quick example, so very theoretical. We have an application that wants to have a specific flow when you're logged in as admin, or let's say a specific role. So is the current user admin? So it's doing uppercase transformation, and because of this uppercase transformation, we might not be able to register for the admin user because it's already part of the system. But we might be able to register for admin with a .i character, and once it's an uppercase, it becomes a Latin I that is ASCII. So this can cause issues. One example of this is the implementation of the hostname validation in Java 6, so an old version of the Oracle JDK. The same vulnerability that I've just presented, looking at earlier implementation, they were doing lowercase transformation instead of the normalization. So it will have the same impact. The only thing is that because lowercase transformation affect mainly the character K, so unless your domain name had a K in it, you wouldn't be vulnerable to this implementation. So it's more limited, but it's still the same vulnerability pattern. Now we're going to look at a vulnerability in a different language, different platform, in the Django. And this is a password reset form that is part of the Django authentication. So here in the form to reset a password, we're receiving an email. We're going to fetch in the next line the user information for this email. So this is we're specifying the email for the user to which we intended to reset the password from. The thing is, we're going to send the email to the original value that was submitted as a form. So it might not be obvious yet, but let's pick an example. So let's say my user, my admin user is super@admin.com. This is the email I've set up. The thing is, a regular user that is not admin could instead submit to the password reset form. So if we submit the first value, it's going to be the admin email that will receive the reset form, the reset link. But if we specify the second value, so this is with the .i value instead of the I in Latin character, then it will fetch the first user, but it will send, in practice, the email to this one. So this is the punycode domain name. So because the service for SMTP in Python sees that there's a Unicode character in a domain, it transforms it to the punycode domain, so the standard way to encode domain for Unicode. And suddenly, while we have fetched the correct information for the admin user, we're not sending it to the right email. And for example, here the admin.com domain might not be available because this is our targeted user, but the admin with the .i, this domain is available. So a malicious user could register the domain and then reset from a Django application the form and will receive the email. So what was the fix? So the fix was in two ways. So they have changed the way they compare the email and the way they fetch user. So this was changed. But more importantly, the logic of the form was changed. So instead of using the original emails submit in the form, they are extracting the user email from the user they have fetched, and this way regardless, so even though there might be a match for another email than the one intended because of the ORM used underneath, here we're making sure we're sending to the email was originally submit when the user register. So this way we're sure we're sending the information to the proper email. So this is the perfect fix because they have done two modifications, and the main one being the logic. So it's cool to see code, but I want to just do a simple demo for the last vulnerability that we just saw the code. So we're going to see it in action now. So here's the demo for the vulnerable Django application. So this is using an old version of Django. The version date to late 2019. It was patched early last year. So our target user will be admin, this admin user with the email superadmin. So this is the staff member, but the idea is that we could attack directly any of these users and reset their password. But we're going to target this one because it's a staff member. So I'm going to jump to the password reset form. This form is public to any user. The idea is you want to be able to reset your password before you log in. So this is going to be the way a normal user will reset their password. So they send their email, and then you have a custom template that says, okay, if your email is valid, you should have received an email and with a link to reset your password. So if we look at just the log of my Django application running on Docker, we can see that an email was sent to superadmin.com. So this is really important. We're going to do an attack on this domain name. Now we're going to submit the same form. So I'm in burp, and I just identified the request I've made. So it should be it, and then we can see the value that we've just submitted. This is just a SSRF token, the big string. So I'm going to send this to repeater, and now I'm going to change this admin for the malicious value that we want. So we already said in the slide the malicious value. So, but to give you an example, here I'm using an application that is basically a cheat sheet. This is a cheat sheet that I've created. It's categorizing different characters by categories. So you can filter, okay, if my application is doing the compatibility mode or the strict mode, then you can switch from one to another. The application is doing an uppercase transformation. What character can have interesting behavior? You can also do a search to filter. For example, here I'm targeting the letter I. I can target the letter K. So which character in Unicode can possibly result as a letter K? So here we have the admin.com domain, and we want to find something that will result as I. So I've just searched it. So because the search in Django is case insensible, we need to focus on either the uppercase or lowercase character. So once I've selected the character, I will get a description of the behavior, and I'll get for different type of encoding the values, because depending on the context, it will not be the same. So here we're doing a request in repeater as a post parameter, so it will need to be encoded with the URL encode because it's a parameter in post. And the way HTTP work is, in general, everything is in terms of bytes, but since the default encoding is UTF-8, this will work. So you don't need to specify that that parameter will be encoded in UTF-8. So I'm going to replace now the Y with this special character here. And what it's going to do, so I'm going to send the request. So regardless if the email is valid or not, I will always get this same redirection. This is because the Django doesn't want to give any hint about if the user exists or not. So, but if we come back here to my Docker log, we can see that it did found a user with the email, but as we saw previously, it sent an email with the reset token to the wrong email address because it used the original email that we put in the field, but it's the same value, but once the email is sent, the SMTP code or email handling code in the Django will normalize the domain. That's why we get this. So that was the demo for the Unicode vulnerability in the Django. Now we're going to look at how encoding can allow us to bypass security filters. I did mention previously that normalization can allow us to bypass some filters. In practice, there are some much easier ways to bypass WAF, and that's what we're going to see in this section. So a web application is a component that is between a client and a server. Your web application will be the backend, and your web application firewall will intercept all the requests, and looking at the user input, it will try to identify XSS payload or potential SQL injection payload, these type of patterns, and potentially block certain requests to avoid certain attack. One way to bypass the WAF and confuse it is use a different encoding that it's not expecting. So by default, most systems will be in UTF-8, but the WAF might not be supporting UTF-8, UTF-7, I mean, UTF-16 or 32. How do you encode in UTF-16? UTF-16 is an encoding that uses 2 bytes for every character. But to use it, you need to tell the system that it's going to be encoded in UTF-16. And the way it works is you need to specify byte order mark at the beginning of the file. So these are magic bytes that will tell the parser this file is encoded in UTF-16. This is supported by most file reader in most programming language, because nowadays modern language support Unicode natively, and they support these type of directive or magic byte. So in the case of Big Endian, we're going to see that every character in Latin will be preceded by a null byte. So if for a sample XML file, let's say we try to we want to test for XML external entities, so eventually we're going to add a doc type that is malicious with special entities. But first we're going to test if our XML file can be parsed in UTF-16. So here we have encoded in UTF-16 Big Endian. And so in Big Endian, every Latin character is preceded by a null byte. But when the application will load this file, it will have the same result as a UTF-8 file with 1 character per byte. We're talking about just Latin character here. Another trick with XML is you can specify it in the XML declaration section the encoding. So you can specify it with byte order mark also in a XML document, but you can specify it in the XML declaration. So even if your application somehow force the XML to be in UTF-8, you can still declare a new encoding and the parser will switch to it. So when the WAF will look at specific thing to blacklist, so let's say a potential malicious path to, so etc password is being read, or a specific doc type is being used, because every character is separated by null byte, it might bypass WAF. Other option to consider, simple option. So for XML and HTML document, you can simply encode with entities. You can use either the decimal, the value, the Unicode value in decimal format, or you can, if you have the hexadecimal code point, you can use the X. So here it's XML entities with the X format in the example. You can also do double encoding. So this is assuming the application does an additional decoding that is not needed. So the parameters are often pre-decoded by a framework, but if the application is doing an additional decoding, then you can do you can abuse this, because the WAF will not have a blacklist pattern for double or triple encoding. In the case of code inside of browser, you might know that if you have an injection point inside of HTML link, you can specify a pseudo protocol JavaScript semicolon, and this will allow you to inject inline JavaScript when a user clicks the link. The application might blacklist for link anything that starts with JavaScript. So one way to bypass this is inserting some non-printable characters. Those characters are simply ignored by the browser. Chrome, Firefox, they will ignore it, and it will be the same as having it without this special character. Also, one thing you can do is only encode few characters. So sometimes the WAF will block specific keyword, encode in different way, but if you encode only a specific character, then it will work. Then you can abuse some parser, specific XML parser behavior, or there are much more advanced stuff, but for now this is still plenty of things to try if you're trying to bypass a WAF. Now we're going to look at how even the database can help us do, for example, a store XSS. So the database will help us to achieve this store XSS by transforming one of our value. We have an example here where the application is inserting, let's say, the description of a user inside of the database. And in our malicious value, we're gonna place an image tag, but here the tag is not lower than, it's actually a Unicode character that look like lower than, but because the database will transform it once it's being stored, in practice it will allow us to bypass filter, because previously with .NET MVC there used to be a request validation component that would block all user input that would include lower than followed by a letter. This can be the component of this can be the behavior of modern WAF. Request validation is no longer around because Microsoft has simply removed all XSS filter from .NET Core, but in their previous version of .NET MVC, they used to have a built-in XSS filter, and one of the popular way to bypass this in the context of .NET was to use this special character this Unicode character called .ff1c that is transformed to the 3c character once normalized. And this test was done with the default Docker image of SQL Server. So you can try it as well if you want. So this is for the context of store XSS. So we send a request, the database transform the value, and suddenly it becomes a valid HTML. So once it's going to display the value that we just stored, then the actual malicious payload will be triggered by the user. We're now going to look at homograph attacks. This technique is a way to trick the user into seeing a domain name, but it's actually a different one, using a special Unicode character that look alike. So what is punycode? Punycode is the way we can now have Unicode character inside domain name. So DNS doesn't support Unicode. It can only be ASCII. But basically we're using a format called bootstring. So we're gonna have a prefix that are is defining that it's punycode. So it will start with xn --. Then the first part will be the ASCII character, Latin character, and then as a suffix, this will be the bootstring system that will define at what position are we inserting a special Unicode character. One example of this is here is a phishing SMS. So it will look very suspicious, but here's it's a phishing domain, but instead of using netflix.com, it's using Netflix with a special I with an accent. So if we look at the actual domain, we'll see here that it's a punycode domain, and if we click on the link, then it would reach a different server. In practice, this is not a really good phishing domain, but still, this is one example. Here's a better attempt, because here's the domain that had even valid the certificate with Let's Encrypt. Here, it's a similar domain to Binance. Binance, I think it's an exchange for Bitcoin. And for the user, it's really a small difference compared to what he's used to. If looking at the URL, we can see that there's only a small dot between the two N. So for a user, it could be analog to just having a dark pixel on their screen, could be some dirt, but they will not necessarily think, oh, maybe there's this weird scripting language in this language that is actually a N with a dot underneath it. So it's not obvious for a normal user to spot these. And what can we do to defend against these? Because this is mostly a phishing vector. Currently, the defense is more on the browser side. So some browser will do some technique to try to find fishy domain. So the way they identify fishy domain is if you try to mix Latin character and let's say a Greek character, they will see it as an attempt to misguide the user. But if all the character inside of your domain are in Greek, then Chrome will allow it. So they try to avoid incompatible language to be used inside of the same domain. So there's still some window to fool the user, but they have multiple use cases that they block. If you are really concerned about phishing, and for example receiving email from a punycode domain that look alike, first make sure that you have SPF, which is something that is unrelated to Unicode, but is probably more important to do regarding phishing. to make sure that the source is really the one that they claim to be. Awareness training will help this. So if users are trained to recognize URL, this is likely to help spot, for example, the first screenshot that I've shown you, the Netflix URL with tons of accent character. With training, they might be able to spot this one. Another thing you can do if you're really concerned about people hosting different domain on the web with a fishy domain, you can actually track the transparency log. This is a log of all the certificates that were created by authorities. So even Let's Encrypt and other provider will all be in the transfer log, and you can query specific domains. So you can do your own queries to spot if people have registered them. And so here's one where Facebook was registered, but it's actually instead of an E, it's a character that is a Greek E for this domain. So by doing a search, you can find potential malicious domain, and then you can contact the provider to take down the domain if needed. So in conclusion, what do you need to be worried about? First, Unicode vulnerabilities are not necessarily as prevalent as, let's say, OWASP top 10 vulnerabilities. But if you are looking for those type of vulnerability, look for upper and lowercase transformation in critical component. These functions are commonly used, but 99% of the time there is no security implication for those functions. Same thing for normalization. We previously saw HostSplit, for example, vulnerabilities that was affected by normalization. Look for interiorization functions, so anything that transforms a domain to punycode indirectly or the opposite. This was the case for the OpenJDK vulnerability, the first one we saw. For security critical stuff like username, service name, maybe role, try to limit to ASCII. This will avoid a risky comparison later on, and yeah, you'll avoid many problems with this. So for basic information and thing that where the comparison is critical, declare explicit encoding when you can to avoid the fact that your system will have to guess the encoding, and you also will avoid potential loss of data integrity if you do a bad conversion and then you lost data. So everything will be available in the slide that I will share again. So everything that you've saw today will be at this URL. You can follow me on Twitter or a GoSecure account to find also the workshop that I've shown quickly at the beginning. You'll find all those content on those Twitter accounts. So if you have any question, I'll be there to answer your question. Thank you.
Okay, thank you, Philippe. Is there any questions in the comments? Yeah, it doesn't look like there's any comments so far. I've got one. Do you find this issue very prevalent with websites that kind of translate back and forth between languages, like English to French and vice versa?
No, actually, like in total, I would say I saw 4 cases of vulnerability related to Unicode. So I present almost all of them in this presentation. So it's really rare. Like the thing that is really prevalent is the section I did for bypassing WAF and bypassing filter. This is something that is more common. So that's also why I did a small introduction on Unicode. This is something really helpful for pen tester, because once they're gonna do requests, at some point you're gonna need to know your details for having proper encoding and stuff. So this is probably if you want to focus on something, first look at the different trick for a special encoding. This is usually more of a use case. The thing with comparison with lowercase and uppercase, the characters are usually very limited. So there's the Kelvin K that has some implication. So even when you find the vulnerabilities, the use cases are going to be limited. Normalization, it's not used that much, so it's something. So when I did my search, I found on the host name verification because there was not that much component using it anyway. So yeah. So yeah, it's regarding prevalence, normalization and uppercase vulnerabilities very low. The trick for a bypass, this is something I've included because it was on the same topic, and this is something really helpful.
Okay, thanks for that. It looks like we have one question from Mike in the comments section here. It's more of a comment. I mean, did you try looking at like other popular frameworks like Rails and I don't know, other frameworks to see if this issue was prevalent there?
No, I didn't. Or maybe because I looked at a bunch of software just looking for uppercase, lowercase stuff. Actually, with the fix, if the logic wouldn't have been fixed regarding the Django, the comparison is still kind of vulnerable because it's matching they fixed the .less-i, but for some reason now it's matching to a whole bunch of new characters because they are doing normalization. So maybe if some function is using the internal function to search user by email, they could be vulnerable again to something similar. But yeah, I know GitHub was vulnerable to this. GitHub had an issue where somebody basically create an account and then it was able to see the same behavior. So if you want to test this, I have not done it because you cannot do this. For example, you cannot target, for example, Hotmail because there's already somebody who registered the domain name with .hotmail with the .si. But as soon as you have a domain name with an I and a domain name in punycode with a special I, then you could see, okay, if I try to reset with so you don't create an account with the special punycode domain, but if when you submit the special character, you receive something on this domain, then you know there's something. So that's one way to test it black box. That's what I saw for there was an article around the same time, so end of 2019, GitHub was vulnerable to this. So again, it's kind of limited because there's going to be very few domains where you can do this. And the attacker, if he does the attack, we know who he is if we can track down who registered the domain, because there's only one. So there's tons of restriction if you want to do those tests. But yeah.
Philip, I guess just to add to that, I think some of those attacks rely on normalization to punycode, right? So what if we just prevent people from registering domains or having certificates signed that start with xn dash dash?
Actually, there's a lot of people who want to have those punycode domain. There's actually a lot of guidelines for registrar. So they are blacklisting special domain that could be fishy. I forgot because I did the research last year, but they have a specific guideline. You cannot register any domain. Like they will have strict validation regarding what you can register. Like if you are trying to register Apple with a E that is Greek, or there are some domain that they will, if they see that there's some collision and there are some pattern that they actively block. Like there used to be a problem with a boot string, so the format of punycode, where in the suffix part, the state, I forgot the detail of how it's working exactly, but you can write it in a different way so that in the end, it's not inserting any special characters. So it would match, if you evaluate the punycode, the same domain. So this is one example where once you're registering a XN -- domain, they have a bunch of validation to make sure it's not an improper boot string and it's well formatted. There are some cases. It's explained in the paper from HostSplit, I think. Is it this one? Yeah, I saw it in a paper. I forgot which one, but basically, registrars are doing some due diligence regarding validating a punycode domain to avoid some known attack. But this won't prevent that. Let's say my company, I don't know, has an I in it. Somebody will be able to register a domain with it with a .i in it, because Arabic country, Japanese, it's widely used in Asian country, actually, the punycode domain. So the idea is to have internationalized domain, because everything else is translate aside from the URL. So for many people of those countries, that's the language they know. It's easier for them, but it come at a cost, of course, of security. And there's different school of thought. Just to give you an example regarding punycode domain, I think in Safari they just don't evaluate. They don't transform it to Unicode once it's being displayed. Compared to Chrome, who supports it but does aggressive validation and sometimes will fall back. If it finds it fishy, it will show it in ASCII only. Firefox will always show it in Unicode, whatever. So there's different strategy, and yeah. So I forgot that the question was about what. I know it was a link to punycode because
That's okay. I think you've answered it. Thank you.
Oh, sorry. I think we have another question as well. This is from Sanya. How can a normal user protect themselves from a punycode phishing attack?
Okay, just knowing about it, if you look at the certificate in your browser, so I took a couple of screenshots of property of a certificate. If you display the detail of a certificate, you will have the ASCII version of it because it's meant for review. So if you look at the domain, it's looking fishy. Other than that, the normal security hygiene, I would say, would help. So if you receive a link by email for your bank, don't click on it. It's not a normal procedure. So same thing for SMS and stuff like that. So because people will always have find creative ID for domain. So don't be too focused also on Unicode. Like people are not that sophisticated. So for example, let's say Apple, people will not register Apple with a E with an accent. They will just create a new domain that is supportapple.com or supportapple.in. So this will look credible, and it's much easier. You don't need to look for a special character. And so while it's one way to do phishing URL, like the Binance one I gave as an example, it's an efficient one, but there's probably other way. Like you can find a clever domain that look like a real one. So if you're doing phishing attack, for example, for a pen test, and you're targeting a company, don't necessarily go for a punycode domain for the phishing, because depending on the browser, it will not be displayed in Unicode for every user. And having just a domain that is the company portal.com will probably work as well, if not better, than if you're trying to be clever with Unicode. So, but from a user perspective, just normal procedure, and just be careful. Don't click on link you receive on email for your bank and stuff. So.
Yeah, I can attest to that as well. We were doing a recent red team where we were looking into that. We were looking into punycode domains for our target, and we found it unreliable. Like Chrome, doesn't want to render it properly. But Firefox will, and like I don't know, we just didn't want to take the chance, because who knows, maybe Microsoft Outlook as well won't render it properly. So in our testing, we decided to, as you said, just choose a domain that looks similar enough to the real domain, and that worked very well. So we don't necessarily need to use the punycode. But is there any other questions or concerns? In the meantime, at Jack or Yukfei, you guys have any questions for Philippe?
I'm good. Thank you.
Yeah, nothing for me either.
Thank you. That was great.
Yeah, I guess we'll give it another minute or so. Where do you think, is there like another frontier of characters to try that hasn't really been looked into from a security perspective? Like, is there anything else to explore here, or do you think mostly that this is a like an understood vulnerability, Philippe?
Yeah, it's pretty well understood. There's not that much cases so far. It's really hard to find a vulnerability that were affected by stuff like this. It's mainly library and framework stuff. Aside from that, there are new Unicode characters that are introduced, but these are not the character usually that will have security implication. Like the weird case with Kelvin, I think probably that people who made Unicode already regret it, so that they won't do the same mistake again of for some reason you transform a special character in extended char set and it becomes a Latin character. So there are a few cases like this. So, and I don't know enough Unicode to know if there are some new feature that will come up that will have security implication.
Okay, fair enough. It doesn't look like we have any other comments in the chat here, so I guess we can call it. So thank you, Philippe, for coming out and giving your presentation. And before we leave, thank you everybody who came out to watch. And like I said before, if you have any feedback, questions, or concerns, leave it in the feedback form. And big thanks to our sponsors: HP, Checkmark, Security Compass, Sonatype, Security Innovation, Amazon, and Shopify. Take care, everybody, and we will see you next month.